All right, Max Planck and Einstein were working on this quantization thing, and they're like, light has particle-like behaviors, and Einstein explained that in the photoelectric effect, called them photons. So de Broglie, he wondered, well, do particles have wave-like behaviors? And won a Nobel Prize for that. So we can take Einstein's equation where he relates energy to the mass by the speed of light squared. And we know we also have this relationship where energy is equal to Planck's constant times the speed of light over the wavelength. And so we can set these equal to each other because they're both equal to energy. mc squared is equal to Planck's constant times c over lambda, which is wavelength. I'm doing this because the problem's asking us to calculate wavelength. All right, you can cross multiply here, get lambda times mass times the speed of light squared is equal to Planck's constant times the speed of light, and one of these is going to cancel out. All right, so divide through by mc, and you got lambda, which is wavelength, that's what we want to isolate, is equal to Planck's constant over mass times velocity. I just changed that c because that's the speed of light, but de Broglie postulated that anything has a wavelength, any particle. So this is called his de Broglie's equation. We're going to use that to solve these problems. All right, so we got a problem here. We got an electron. Let's do this in red. Electron red. Given the mass in SI units, speed in SI units, great. Get the wavelength. And then we're going to compare that to, let's go with green. For the ball, mass in SI units, speed in SI. All right, perfect. Everything's SI units. So our answers, the units can get a little hairy, but you know that because we're using all SI units, base units, all right, the speed is derived from the base. The answer is going to be in meters because meters is the SI unit for length. All right, but let's do the units. Show you how to cancel them out anyway. All right, we'll do the electron first, so we'll do that in red, right over here. I'm going to kind of go sideways here, get more room. Wavelength of the electron, wavelength of the electron, right, is equal to Planck's constant. Wait, what are we doing here? That's right. Sorry. Mass times velocity. Mine went blank for a second. All right, Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Now, I'm not going to use joules because there are no other joules in here. So joules is a derived unit. We learned that in the first week or so of our course, but you don't have to remember this. But joules is kilograms times meters squared. Now I'm going to run out of room. You know what? That's fine, because that's all we have on the numerator over second squared. All right, times seconds. All right, all of this is joules. So Planck's constant has units of joules seconds. And I just broke down joules into its base units. Look, if this doesn't make sense, just know that your final answer has to be in meters because it's asking for wavelength. All right, so I'll just kind of do this neatly. All right, mass goes on the bottom, so it tells us the mass of the electron is 9.11 times 10 to the negative 31 kilograms. Very nice. SI unit. All right, times the velocity is 1.0 times 10 to the 7 meters per second. So move that per second up here. And you'll see everything cancels out nice. All right, so there's a meter there. One of these canceled out, so we're going to be left with 1 meter there. One of the 2 meters there. All right, kilograms is going to cancel out. There's a second square there, then so everything cancels out except for that meters. All right, let's just punch these numbers in. 6.626 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 divided by 1 times 10 to the 7. Oh. Yeah, that's good. All right, so the wavelength. Oh, yeah. So this is expected. So that's in the range of about 10 to the. That's about how the wavelength of an electron. 7 point. We need 2 significant figures. We don't want to got 2. What was it? 7.3 times 10 to the negative 11 meters. All right, that's the wavelength of this electron, not all electrons, because you can accelerate them at different speeds. All right, I'm going to try not to get off topic. Ball is in green. Let's do the same thing right here. Now, there's going to be much shorter wavelength, right? Because ball is much bigger than an electron. All right, so we got the same thing here. Planck's constant, 6.626 times 10 to the negative 34 kilograms times meters squared over seconds squared times seconds, because this is all joules, and Planck's constant is joules seconds. Again, if you're getting lost with the units, then just put it in meters, and it's fine. The mass goes on the bottom with the velocity, and it's 0.1 kilograms, 0.1 kilograms, and the speed is 35 meters per second. Meters per second. Right, because per second, I'm going to reciprocate that up there. Okay, kilograms cancel out. Seconds squared on the bottom. Seconds times seconds on the top is seconds squared. Cancel out. One of those meters cancels out one of those, and you're left with meters. Like, that's the unit for length, wavelength, in SI units. Calculator. Hello. All right. 6.626 times 10 to the negative 34 divided by 0.1 divided by 35. All right. Like I said, very small wavelength. 2 significant figures, 1.9. Wavelength of ball, 1.9 meters. Oh. Not meters, that's times 10 to the negative 34, I think it was, meters. Okay. So compare it. The wavelength of a ball is much smaller than the wavelength of an electron. The wavelength of an electron matches the size of like molecules, things we can. That's what makes it possible to see atoms and molecules, because we can use electron microscopes, because electrons have a wavelength appropriate foreseen things that size.